I am going to talk to you a little bit about the Science Operations Center development. This is going to be a little more technical and dry, but I think we're going to address questions that people have been asking. So I hope we cover some stuff that's actually of interest. And I really want to call out the team that is working on this. I'm speaking, but almost all of the hard work has been done by Matt West and Jillian Redfern and Chris Lauder and Marcus Hughes. So this is very much a group effort. So I just want to remind you what PUNCH does. Now, we've seen this slide and I think even more interesting versions of it already, but I think it's really important to understand what our job in the SOC is in producing data products to look very carefully at the observations we're getting. And so, as you know, PUNCH is observing continuously with a 4-minute cadence, and it has 4 different observatories that all fill in different pieces of the sort of total puzzle that we're trying to fill in. We have NIFI down here, and then the 3 WIFIs out here covering a range of about 5.5 out to 180 solar radii that form these trefoils of sort of three panels plus the inner part from NIFI. And PUNCH is going to produce both these sort of small mosaics and then full mosaics where we fill in the entire gap. Over the course of an orbit, you get a few of them. So I already mentioned what PUNCH is composed of. PUNCH produces a lot of data products. There's individual images calibrated at different levels from each of the different observatories. There's these trefoil images. Then there are a whole bunch of derived products, and I'm going to talk about these in detail in a minute, so don't worry that I'm going fast. And then in addition to the sort of the main science products, there are going to be low latency space weather products to support space weather forecasting. And they're going to be quick look products, as we talked about, for applications like HelioViewer and JHelioViewer. And there's a whole bunch of different formats. There's just clear images. There's images in different polarization states. And then as you go up into higher levels, we get brightness and polarized brightness pairs. So there's going to be quite a lot of data. In fact, there's a lot of data and a lot of processing. It's quite complicated, and this is the processing has been updated a little bit since this figure was put together. But I think this gives you a sort of a good overview of how complicated PUNCH's data pipeline is. It's much more complicated than I think typical SOCs for instruments that are just a single camera making a single observation. There's a lot of complicated work that we are figuring out how to do right now in the SOC. And let me walk you through some of the different processing levels and the steps that go into it, just so you have an idea of what we're trying to do. So we start with raw telemetry from the spacecraft. We turn that into images that are uncalibrated, and then we have to work through quite a number of steps to produce calibrated images. We have to remove a flat field. We have to remove spikes that are unwanted. PUNCH operates in a shutterless format, so there are streaks that are produced by the readout from specific structures. We have to do destreaking, which is actually similar to something that has been done by stereo, but it's a challenge. Then we have to subtract the stray light that we can measure, the instrumental stray light, and then finally we have to use the star field to determine the pointing. To generate fully calibrated images and camera coordinates with all of the image registration data that you need in WCS compliant, that's World Coordinate System compliant metadata, so you can connect these images to your observations and we can connect them to make mosaics. So that gets you to level 1. That's already pretty complicated. From level 1 to level 2, now we do some of the work to resolve the polarization states and integrating images into trefoils, while marking via FITS extensions where there are artifacts in the images caused by the presence of the moon or other stuff that we don't want to see, so that when you're working with these for science that you should exclude certain parts of the image from your analysis. That brings us to level 2, which is polarization resolved NIFI and WIFI trefoils. Then we have a processing step to level 3, where we remove the F corona and star field background. And there's an important hitch here, which is that we have to build up these backgrounds before we can do this removal process. So there's some built-in latency between level 2 and level 3, and you won't get these images right away we'll sort of work on getting them as fast as we can, but the ideal time frame is something like 2 weeks to build up the background, I think, and we'll sort of figure out exactly what's optimal as we go. But finally, you get these beautiful background subtracted trefoils, which then can be combined into a whole bunch of level 3 products, solar wind speed maps, these mosaics that I just showed, and then nifty, high quality, low noise mosaics, and the full frame produced every 32 minutes. So it really is, there's a lot of data products. There are some complicated loopbacks where we have to produce part of a product, measure the background, go back, subtract the background, proceed onwards. So this is a major effort, and we are thinking very deeply about how to do this smart and right, and make sure that the data products are as good as they can be. But okay, it's complicated. It's not that complicated. We take camera images, we calibrate them, we put them together mosaics, we remove the background and put them together into a couple of sort of key products, which I think are the ones people are going to be interested in. And our primary products that we're going to produce with our data reduction pipeline will be the level 1 products and the level 3 products. The level 2 products, we probably will be able to make available. They're sort of an intermediate product, but we're also going to put all the code out there for our data reduction pipeline. And I'll talk about that in a minute. So that if you want to make some special version of a level 2 or some special processing on a level 3, you can run your own pipeline. So we've been thinking a lot about the data flow architecture. We've gone through a couple of iterations now, but I think we're sort of coalescing onto an approach that's going to work. We've spent a lot of time talking to people who've developed other data pipelines and other missions, and bringing our own past experience developing these to try to make choices that are really going to result in sort of a high quality internal data flow pipeline for us, but also a really good external experience for people who want to do their own custom processing. And I have this schematic of how we get data to go from level 0 to level 1, just to sort of illustrate a couple of sort of key points that I'll talk about in a little more detail in a second. But a really important one is we're going to use this workflow manager called Prefect. Prefect is Python native. And so one of the big advantages is that as we develop these recipes, we're calling them, for calibrating or producing other data products that we're going to store in a cookbook, Prefect can run these in our pipeline environment, and you, because it's all Python native, will be able to download our Python package and run them for yourself seamlessly as if you're in the SOC. You may not have access to our databases and stuff, but it will provide very straightforward ways that you can find the right data that you need, put it into this recipe, drop it into Python, and make a level 1 file or a level 2 file or whatever you need. And I think this is going to be a huge advantage to making sure that the SOC can meet multiple needs at the same time, the needs of the sort of data production side on the internal to the Punch project, and users external to the Punch project. So Prefect will detect level 0 files. It constructs the recipe that says, this is the file to produce, these are the steps. It executes those in Python, writes a file, and then we update it, we put it in our databases, and the databases provide hooks into the VSO and other places so that you can access our data directly wherever you are. We've sort of come up with this maybe a little bit too cute way of thinking about this, but for people who aren't familiar with data pipelines, I wanted to sort of go over exactly what goes into building one of these things. And the first step is that the pipeline gets in the segments. So the segment that produces level 1 files or level 2 gets invoked by a control segment who we call the chef. That's going to be built, as I said, in Prefect. The control segment carries out workflows, and those are sequences of processing steps, a recipe that generates our specific products. And the recipe also instructs the workflow which parameters to work with, which files. So, you get the right files, the right 4 observations to go in your trefoil or whatever. We call these ingredients, and what order to use them in. And then finally, the control segment picks the appropriate recipe from the library, runs everything. We call the library where we store these the cookbook. We're making Punch here and Punch products. And so we'll have a whole bunch of Punch recipes, and all of these will be available to you externally in addition to us internally. So we've spent a lot of time thinking really carefully how we can make the best tools and the best products. And we've come up with a list of sort of principles for our our activities in the SOC to try to constantly focus us on what is best for the community. We have a couple of sort of key principles that are drawn from data stewardship principles and software development principles. So accessibility, right? That whatever you're using will be well documented and self-describing, so that if you get a piece of code or a product, you can figure out how to use it. You don't have to dig around for the documentation. That's one of the big challenges we've seen with missions in the past that we want to sort of help solve with this one. Longevity, we want to make sure that these tools and these data remain usable after the mission ends. There's going to be nothing that you need to work with our data that might disappear from the environment. And we're also going to very carefully archive everything you do need in the NASA SDAC, so you can access it no matter what. Portability, we're going to make sure that the tools work on different platforms, different analysis environments. If you're in SunPy, if you're in SolarSoft, we're going to do our best to make sure that you have a seamless experience working with Punch data. Traceability, we're going to make sure that the tools document where they came from. So if you're working with a level 3 product and you can't figure out why it's messed up, you'll be able to trace back to the individual observations to diagnose, oh, there's an artifact here. Okay, I understand. Transparency, as we make improvements, we're going to make sure that you can understand which version of the file you have, what improvements there are. We're going to really make sure that changes in calibration are well documented. And then finally, security, we're going to comply with all of our own internal mission assurance and security requirements. In particular, these principles inform a data product strategy where we've gone around and talked to a lot of people in the community who've developed products and are really trying to implement best practices. We're going to make our products in FITS. That seems to be the standard that everybody's familiar with. It works with all of the community tools. That's going to be the same. We're going to have the same formats for our calibration products, our data products, and intermediate products. It's all going to be in FITS. And the internal data handling that we're building in our software will also expect FITS files and work with FITS compatible tools. So everything should be really seamless for you. We're going to make sure that we're fully standards compliant. So there's not going to be any weird things in our files that trip you up. We're going to do our absolute best to support open source community tools like AstroPy and SunPy, working with those communities. If we do something custom, to make sure that there's support for SunPy maps or whatever, they will work with Punch data. And we're really looking at a bunch of community best practices. I've just highlighted this one really nice poster from I think an SPD meeting a few years ago, showing sort of how to construct FITS headers that are transparent. And we're gonna do our best to follow those principles. So when you get a Punch product, you can look at it and understand what's going on. I already kind of went over the data products, but just to remind you, there's level 1 products that are sort of camera coordinates, single data frames. And then there's level 3 products, which will be the NIFI images, the trefoil images, composites that fill in the gaps. We'll use secondary HTUs to flag non-standard data. I talked about that. And then we have ancillary products. You'll be able to get our background models and so on and so forth. We're going to make the code to the extent that we can available in SunPy or SunPy affiliated packages. So if you have a special processing problem, you'll be able to get our code and do your own special processing and get what you need. The data, people have asked about the accessibility of our data. I want to highlight a couple of really important things that Craig and others have already mentioned. We're really trying to be radically open in this project. Everything we make is going to be available in some way. I can't promise every last thing is going to be in SunPy, but it'll be on GitHub. If it can't be in SunPy, it'll be available on our website, on the SDAC. All of these things are completely open to the community when they're produced. There's no embargo period or anything. Our primary, let me go back. Our primary data repository is at the SDAC. We maintain a secondary repository at SWRI. Both of these will be hooked into the VSO, so you can find those products, user tools through SunPy, data reduction software, and all the documents and support software you need should be available through Python package managers, and we hope SunPy. We're talking to that community right now to try to make sure we can fully integrate with them. And we're going to make sure that the standard tools support our data. So if you need something special to make a SunPy map out of Punch, we'll make sure that's in SunPy when those maps start, or when those products start flowing, so that you can just open up Punch, make a SunPy map, and do your analysis. And yeah, importantly, also the data will be accessible via the VSO, and we are actively talking to them right now, so that should be possible right away. Now I want to pause on this slide for just a little bit longer than the other ones and really try to get you as users to think carefully about this one. We need your help. And a couple of ways, we've highlighted a couple of ways that we need your help, and people in the discussion have brought up other ways that I think we would like to engage with this community right now. Really importantly, we're doing our software development right now. And if you have sample data or model data that you want to send to us to make sure that the tools we're developing are going to give you back what you need when you have real punch data, we'd love to hear from you. We're very interested in different data sets that people like to use in our testing to make sure that we're getting you the products that you need for your particular problem. So get in touch with me or ask questions in Slido or whatever, and we'll work with you to make sure that we can run your data through our pipeline. I really want to engage people to help us avoid pitfalls that we've encountered in other missions. So if you have lessons learned, if you worked on Stereo Core 2 or High or C2, and there's something that you think, oh, we could have done this better, get in touch with us. We would love to draw on your experience. And if you don't get in touch with us and you worked on one of these missions, you may hear from me anyway. Another thing that we're going to be doing as we go is developing sample data products and soliciting feedback from you guys in the science community on the usability, the format, if we're missing metadata that you really need. So we will put these out. I don't know exactly how we will put them out, but as soon as they're available, we'll sort of communicate with the SOC science team, the Punch science team, and people in the broader community to get some feedback and try to improve the products so they're going to meet your needs. And
bing, bing, bing.
Same thing with our.
That's your 2-minute warning. Bing, bing, bing.
Thanks. I'm almost done. So the same thing with our analysis tools. We're going to make these available on GitHub and in other ways, and engage with you, hopefully, to get feedback on, oh, I can't do this thing. I don't understand how to do this thing, whatever it is, and make sure that those are meeting your needs. And I think I'll just put the summary up. I don't have to talk to it specifically, except I want to say this bold thing at the bottom. Again, we're really seeking active involvement. I think it's really important that we hear from you and make sure we meet your needs. And I think I'll just stop there. So thank you.
Thanks, Dan. That was awesome. I think actually that's great. You covered a lot of the questions that were in the Slido from this morning, a lot of the things we had to say about that. We do have like 1 or 2 minutes because when I binged Dan, he stopped. So if anybody does have a live question they want to raise their hand and ask of Dan.
I saw there was a lot of action in the chat here. I wasn't able to keep track of it, so I don't know if there were Slido questions or chat questions that I missed.
There's a couple, maybe the Slido question, did he answer like Gilly's one or the first one about the seam?
Can you just say what it is, Sarah, please?
Okay. Or maybe Gilly, if he wants to raise his hand and ask it. And apologies if you did answer it, sorry.
Yeah, Gilly, go ahead.
Yeah, I just noticed on one of your one of the slides that like right at the very end, you were putting the NIFI interior to the WIFI, and it looked like there was still a seam there. So I'm wondering, is there going to be radial like normalization and matching there? Craig nods yes, maybe.
Yeah. So I did not make those slides. They were made up a long time ago, so I can't speak to why that seam is there in those. Maybe just the limitations of the different sort of data sets they use to generate them. But yeah, no, the idea is that the products will be more or less seamless when you get them, and we're going to work really carefully to make sure that the calibration is right and the resampling is right when these things fit together. So when you get one of the Punch products, it's just going to look like as if it was taken by a single super
big
special
camera
telescope that can do all this stuff really well.
Yeah, sure. Well, let me know if or when you're working on that part of it you're asking for input. That's the stuff that seems fun to me. So
yeah, we will certainly be engaging people to talk about sort of what are the best ways to do this, and I think Barbara also mentioned what other tools do you want to work with the data, or what other processing or whatever, and we can we look forward to sort of hearing from the community. Oh, I made this tool that radially filters punch data. It looks awesome. We can put that, we're going to be open source, so we can put that into the analysis tools, into SunPy and so forth. And Craig has his hand up, so maybe he wants to say more on this.
Yeah, I didn't want to interrupt you, but I want to point out these seams are really I mean, we spent a lot of time thinking about this. Getting rid of those seams is a really critical part of punch. And so to make that happen, we're doing a couple of things. Dan talked about the uniform PSF step, where we transfer the PSF to an artificial instrument with a uniform PSF. We're doing quartic photometric calibration, which, you know, I've never heard of in a science mission in space before. Most people do linear and stop there. And we carefully arrange the fields of view so that every one of the cameras overlaps with every other one of the cameras, so that we can get continuous cross calibration. So these features hopefully will enable Dan to actually deliver seamless data products. We've set the stage.
All right, thanks everybody, and thank you, Dan. So we're going to move on to our Shine style discussion, which basically means we're going to have a series of quick, short talks. Really, the purpose is just to seed more discussion, any points from this morning that we want to come back to, but then there'll be new points brought up. And Barbara is driving. Thank you, Barbara. All right, so actually, yes, I will start. Session organizer's prerogative, but actually what I'm going to start with is to summarize the flow mapping meetings. Barbara mentioned these this morning. So just the background is, as we've been discussing this morning, we require flow maps for answering several of the punch science questions. We already have a solution for that. The punch proposal already prescribed, tested, published techniques for meeting this requirement, namely the 4 altitudes between 5 and 80 solar radii at a 6-hour cadence. And so that's the piece that is required to be delivered by the SOC. But the purpose of the flow mapping technique workshops is to do better than that. We can do better than our requirement. We can do the best we can. And so that's what we're trying to explore. And we also don't need to reinvent the wheel. We know that there are experts across heliophysics who have other techniques. And so we're trying to leverage that. And you're going to hear about that from Bea and Raphael during their talks tomorrow. So we had sort of an informal pre-workshop of August last year, just with some team members from that are located in and around Goddard, just to sort of pre-test some of these tools. And then we had our first formal workshop in November of last year. And then we had a follow-on one just a month ago in July. And the Punch Associate Investigators, Raphael and Bea, really took the lead on the July one. And so they really did an awesome job with that. Next slide, Barbara.
I'm trying. Come on, come on. There it goes. Okay.
There it goes. So the purpose is there are a plethora of different techniques out there, and they each have strengths and weaknesses. And it's not that one is better or worse. It's that some are better or worse for the particular science that we're after. And so that was what we were trying to quantify. We, as Barbara said, we want to be ready to hit the ground running on this. So we want to have all these tests done now. We want to have decided which tool for which science question now. We want to have the error and uncertainties quantified now. We're using real heliospheric data to test this. That Core 2 deep field is one. Bea is going to talk about using the Aurora though, and Raphael's technique is based off a photospheric flow map. So this is really leveraging sort of different kinds of tools. And then we're also testing on synthetic punch data where we have the models behind that to really know what the ground truth was. And even if it's simplified, the point is we can back out what the real answer was. There's also this Middlebury optical flow benchmark data set. And after I get done, Valmir and Vadim are going to talk about their flow mapping challenge. Next slide, please. So Barbara mentioned these two, the 4 kind of general techniques that we're after. The first kind I called it measurement type 1 was what measurement technique gets the best answer for the in general solar wind, like the bulk solar wind, the global scales, what captures, even if there's a large spread, what really gets that the average solar wind right. But then the second thing, we're really after steep gradients where there's flow shears, where there's maybe it doesn't represent the bulk solar wind, but it's where turbulence might grow because there's this massive gradient in the flow. So that's a second type of measurement that might be achieved with a different kind of tool. The third is relating it to the big singular structures like a big CME and how the measurement 1 and measurement 2 relate to that big structure, like a CME. And then the fourth one is for, you're going to hear more about this from Steve Cranmer on Thursday, but the inward flows, getting that inward component for the alphane zone. Next slide. So this is what Bea and Raphael came up with after the July workshop. Really a lot of great stuff happened, and we'll be hearing more about this from them and more about this later today. But optical flows, physics informed method, they have all these different techniques and tools that we heard about. We really talked about how important it was to characterize the error on each of these and quantify them. And by validating them with these different challenges, we started talking about how to make these punch data products. And really the model and the simulations are going to be a key part of all of this. Next slide, please. So we also talked about machine learning and how that could be integrating and the limitations of all flow tracking, namely the aperture problem, and then waves versus actual transport of mass, and how do you disentangle those? I think, again, we're going to be looking to models to help with that. And then Dan already talked a lot about this, how we're going to integrate with the Science Operations Center. There's the requirements we have to deliver, but then there's also going to be tools that people are going to be working on that they might want to share. So with that, I think I'll hand it over to Valmir and Vadim to talk about their flow mapping tracking challenge.
Actually, Valmir was hoping that he could do the introduction of his talk first and then do the flow mapping.
Oh, the opposite
challenge.
Order. Yes, please.
Yeah,
yes.
Yeah. And so, Lakshmi Chita, I know we had you first. If it's okay with you, can we go ahead and start with Valmir's talk, and then he can do so that he can set the stage for the flow mapping challenge, and then you will be second. Is that okay for everyone?
Yes.
Excellent. Thank you very much.
Hi guys. So I thought that I had to use my slides, but thank you. It makes it easier. I can put my notes on. 1 second. Sorry. All right. Hi everyone. Good morning. My name is Valmir Moraes Filho, and I'm a second-year grad student at the Catholic University of America. And today I'm going to present to you the model that me and my collaborators have been working on. This is the synthetic corona outflow model, or SYNCOM for short. Is an empirical model based on statistical measurements of real data. The SYNCOM is a result of our own efforts for measuring the corona flow velocities using the cross correlation of 1D signals as our algorithm, but we didn't know if we were hitting the target velocity, the desired target velocity. So also, we noticed that the PUNCH community is in need of a model that validates and compare their algorithms to better assess their strengths and weaknesses. So we came up with designing the SYNCOM, which uses Gaussian waves as its main engine and requires some parameters from real data to generate a synthetic distant time image. These parameters control every aspect of the Gaussian wave, like height, center position, and width. Can you change to the next slide, please? Thank you. We have been working with data from the Spectrum campaign ran by Stereo A and Core 2, and these images have been prepared by Craig DeForest, which resulted in a very clear flow throughout the whole field of view. But before we used these images, and extract the parameters, we had to transform the image coordinates from spatial which is height and position angle, to spatial time, which is height and time. In figure 6, you will see two distant time images. On the left is from the real data, and on the right is the synthetic image generated by the parameters from table 1. So I'm going to talk quickly on how I obtained the parameters. First, the height of the Gaussian wave is controlled by the maximum brightness of the real data. And to reproduce the same brightness behavior, we performed a simple linear fit of the log of the mean brightness across all position angles by the log of the cube of the radial distance. This resulted in a very clear power law, which is decreasing, that you can see in figure 7. And moving forward, we see in the data a quasi-periodical behavior that we can see, and then we performed, as I like to say, a frequency exploration. I did represent the frequency exploration in figure 8. We were looking for a characteristic frequency in the real data that will translate the average periodicity in the number of features observed in the distant time image. So we took the power spectrum of a signal emitted at the lowest radial distance at all times and extracted the maximum frequency for each position angle. Due to the presence of a CME in the position angles from 37 through 80 degrees, we removed these position angles from our analysis. So the estimated frequency was taken by thresholding the frequency, the maximum frequency, by the detrended power. And for our center position and the width of the Gaussian waves, we performed, they are controlled by, don't move, wait. They are
Sorry, I was
controlled
trying to
by
get
the
rid of that stupid X thing.
They are controlled by the velocity and the velocity standard deviation. The acceleration of the velocity was done by taking the cross correlation of two signals, of two 1D signals at different times at the same position angles. And we obtained a velocity estimation by thresholding the velocity measurements by the maximum cross correlation coefficient. And this estimation could have been done by any other method. So the values that I have for my algorithm could have been provided by any other method, as long as it could give me a velocity and the velocity standard deviation, it would be fine to use any other method. Next slide, please. Okay. Thank you. In June, we launched a mini challenge during the second flow tracking workshop using the code written by Vadim Yuritzik. And this challenge basically consisted in a synthetic distant time images that contained a predefined frequency and velocity. Some models have different altitude ranges and different time cadence. And what do we want with the challenge? We want that flow trackers and whoever is enthusiastic about it to test their own algorithms to find the velocity, which is our primary goal. And as a secondary goal, the velocity uncertainties, the average period, and the uncertainties in the period. Right now, we have 7 models in the website. The first is a very basic model that there is no radial decay, no uncertainties, and we already tell you what is the predefined velocity and the average period. So basically it's just for you to try out and see like, oh, I got the value, correct value. And as for the other models, the other 6 models, some of them have velocity and period uncertainties, and some of them has different levels of noise. So basically all of them has noise, but at different levels. And in the website, we also provide the FITS files and the or IDL save files. So you can download them and try out as best as you want using Python or IDL. And basically, so we are inviting all of you who want to try out our model to submit your answers by email, either to me or Vadim, so we could give you some feedback about how accurate and how accurate your attempts were. As for leaderboard and awards, we are still discussing about it, but keep in touch because we're going to give you updates for that. I also have added a QR code of the website challenge in case some of you want to take a look right now. You just like use your phone and do it. I also have the website in the poster. I'm going to put on the chat. Thank you, Barbara. Ahead of me. And as for future plans with the model, we want to implement some additional features like noise, variability in frequency, brightness, include radio acceleration that translates the increase with altitude. And most of all, we want to create a time series of synthetic punch images that use spatial in a time series, which will allow a more broad set of algorithms to be used with the model. Thank you all for listening.
Thanks so much, Valmir. So I believe that the flow tracking challenge is something we're going to revisit probably in our future flow tracking workshops too, as we continue, and this will continue to be one of the metrics that we use. So that's really important. We are going to the flash talks now, so please post your questions to Valmir, either about his talk in particular or about the flow tracking challenge in Slido, and in the discussion session, we'll come back to that. And now we'll hear from Lakshmi Pradeep.
Thanks. This is a great meeting, and I thank my collaborators on this. And probably you don't need any introduction to this topic, but I would just like to point that there has been a lot of interest to connect the features that we observe in the low corona to what we see in the heliosphere. And I think this talk fits right into that particular arena. Could you go to the, let's sort of second slide, the slide after? Yes. No. The slide after? Yes, this one.
Sorry, this was supposed to make it easier on you. I apologize. It's been
no, that's fine. Perfectly fine. I think Sarah already posted a link to the paper of Dan Seaton and co-authors about a nice observing sequence recorded by SUVI, the solar ultraviolet imager on GOES in 2018. The observations are the first ever long-term observations of the extended, or rather middle corona. In the top left, you can see the solar disk in the center and the signal of UV structures and loops extending all the way to almost 2.7 R0 from the sun center. Now, of course, there is a lot of richness, and we have to filter out this richness to get meaningful information. And when we were looking at the movies, one thing was very obvious. So the active region and the coronal holes that I marked there are the prominent features that were recorded by SUVI multiple times. So when the same system appears on the west limb in the bottom in the blue colored image, bottom right, you could see that some finger-like protrusions appear in the corona. So this we call as complex web of coronal structures, and it will become clear why we call those that way. And when the same structure then rotates back on the far side and appears on the east limb, you could see that the similar structures take over in the corona as a prominent features. Now, we know that both coronal holes and active regions are thought to be the sources of slow solar wind. And this particular data set then gives us a very good opportunity to delve a bit more into the reason or the kind of process that are happening at some height in the atmosphere that we cannot often observe, and relate them to solar wind structures. So in the right panel, the grayscale images sort of give you a flavor of a particular event that we call that is a driving of a slow solar wind stream. Now you can see in the panel A that I marked, there is a small arrow which points to a wind stream. It has been long known that these kind of wind streams are passive tracers of slow solar wind. And in the middle section of that figure, panel C shows the repetitive eruption of this particular wind stream. And what we noticed is that these wind streams are ejected when a system of loops or structures in this complex coronal web start interacting and form transient closed loop like features. And that is when we see the ejection of the material outward. And in this static presentation, I do not have movies, but if you have some follow-up questions, I will be able to also show movies. Now the question is, why is this, or what is the reason of this complex coronal web? Then can you go to the next slide, please? The reason is quite simple, actually. So Aleda already presented a nice scene setting talk of how various features in the solar photosphere can give rise to magnetic topologies in the solar corona and in the heliosphere. And that is what is happening right here. So in the white box on the top left, I kind of mark the coronal holes, the two coronal holes with white circles and the embedded active region. So the structure that we saw in the middle corona is basically overlying this simple system of coronal hole active region system. And the interesting part is that the heliospheric current sheet, which is indicated by that yellow line, it's basically the polarity inversion line at 2 solar radii above the or from the sun center. You can see that at the location where it's dividing the coronal holes, it is running almost north-south, meaning that the current sheet is highly tilted. And this highly tilted current sheet, when projected on the sky or in the plane of image, displayed these exciting finger-like structures that continually reorganize and reconnect and seem to drive the slow solar wind streams. And the interesting thing is that this system is a very long-living system. We could trace these structures for 135 days or longer, meaning that several solar rotations. The left top, the top right image then shows the same synoptic view, but now after 3 solar rotations. So you can see the Carrington rotation number increasing. And the important aspect of that particular map is that it actually coincides with the Parker Solar Probe's first perihelion. And the Parker Solar Probe was magnetically connected to the coronal hole on the west, meaning the rightmost coronal hole that is marked in that top right panel. In any case, this just shows that having a simple heliospheric current sheet that is tilted can give rise to these interesting structures where reconnection seems to persistently drive. We also supported our claims with an empirical data-driven MHD model, which shows the kind of magnetic topologies or connectivities of S-web arc and the heliospheric current sheet shape in the lower left panel that resembles very much similar to the polarity inversion line we got. Now, if we go to the last panel, last slide, sorry. Of course, SUVI doesn't observe all the time, and we don't have also the heliospheric view. So we complemented SUVI observations with stereo observations. Because this is a long living system, we can view this system from stereo on multiple epochs, during multiple epochs. And the top panel is the time when stereo was able to see this coronal hole active region when it was facing the Earth, but at the limb view of the stereo. So those stereo UI image doesn't have the extended field of view. You can see the similar finger-like structures protruding all the way into the heliosphere. And the same structure, when appeared during or just days before Parker Solar Probe, again continued to give a similar appearance in the heliosphere. Now, for reference, I marked with the symbol the Parker Solar Probe approximate position in the plane of sky. So it would have tracked features like this when it measured the highly structured slow solar wind emerging from the coronal hole, which is what the SUVI also observed. So with this, I would like to conclude and take any questions, but I would like to emphasize the importance of middle corona in connecting the sun and the heliosphere in a much quantitative way. Thanks.
Thanks, Pradeep. So please put questions to Pradeep in Slido, and we'll have a discussion after the break with everybody. So please record your questions to Pradeep in the Slido. And we'll go ahead and move on now to Richard Morton.
Can you hear me okay? Oh, excellent.
Yes.
Thanks for giving me the opportunity to talk today. So I'm following on from kind of Pradeep in emphasizing the importance of understanding what's going on close to the sun. And I'm a little bit lower down than him in what I'm going to call the low corona, and this is the corona that's sort of very close to the surface of the star. And what I'm really interested in terms of my research is looking at sort of the alphenic waves and fluctuations that originate in the low corona, or that we find in the low corona at least. And what I'm going to talk about is how we can use observations of those types of waves to maybe provide some extra information for kind of the PUNCH observations about what's coming out of the sort of solar surface and coming through the low corona. One of the important things that we see is that the low corona is very finely structured. So you can see that in this image on the left. So this is just from SDO and it's been enhanced in a certain way. But you can see that there's this fine scale structuring throughout the corona, and it's kind of transverse to the magnetic field. And this is not just sort of confined to active regions, which I guess is where it's typically been studied, this fine structure. But you can see it's everywhere. The quiet sun, the polar regions, there's all this sort of fine scale perpendicular structure. If you could just move to the next slide, please. So here I just have an example of sort of some, I guess, highly processed AIA movies on the left-hand side, where I'm looking at a polar region in the coronal hole, and you can still just about see that there's this, this fine scale structure in there. So the top panel shows your typical view of a polar coronal hole, and you see your large plumes in there. But it turns out each of these plumes is made up of much finer scale structure. So there's this transverse structure to B, and essentially it's, well, I think it's some kind of density enhancement. So in EUV, you expect your emission to go as sort of electron density squared, and we see this sort of enhancement in intensity in EUV. So it suggests we have this density structuring perpendicular to the magnetic field. And it turns out this is very weak in coronal holes. It's sort of on the order of 2% of the intensity, which is why it requires sort of this processing to bring it out. But what this structuring does is it actually allows us to measure waves as well. So in the top right, I just show a time distance diagram from AA that we see in 171, and below it, I show the results of sort of the extraction of waves using some routine we have to do this. So you can see the structures are sort of constantly swaying side to side, and this is alphenic waves, or if you have this perpendicular density structure, you'd probably call it a kink wave, this kind of swaying motion. So we can pick up that in AA, and we can also see it when we look at infrared images as well, so from the ground. And in the bottom right corner, I have a Doppler velocity movie from the coronal multi-channel polarimeter, or COMP, and this shows the corona in about 1.3 megakelvin, and what we're looking at is, as I said, the Doppler velocities. And what you can see is there's this signal that's constantly propagating away from the surface, or away from the sort of low corona. You can't see the disk of the sun because it's been blocked out, but you can see these black and white periodic patterns that are constantly moving up from the occulting disk and outwards. And this is the alphenic fluctuations of the corona as well. So can you go to the next slide, please? So using these measurements of alphenic fluctuations, we can provide a number of different products that might be useful for sort of working out what PUNCH sees higher up. So with that comp data, I think that's really the best way to use the alphenic fluctuations. So on one hand, you can measure the sort of the nature of the alphenic fluctuations that we're seeing and the signatures of the turbulent driving much closer to the corona. So you could do this in the photosphere, but all the waves have to come through a rather messy chromosphere, and that's going to change, well, at least in my opinion, it should change the nature of the turbulence that's sort of coming from the photosphere. So when we look in the corona, we get this signal that should really kind of stay and propagate out maybe into the heliosphere. So you can do that through measuring power spectra of these velocity fluctuations. And here on the left, I just show an example of that, where we see these different power law type behaviors. And we see they have a range of spectral indices, which I've shown in the histogram in the bottom. They kind of span from sort of -1, which is seen in the solar wind in the energy ejection range, to sort of -2, which is towards the end of what we'd expect for some kind of turbulent behavior. These power law indices belong to different structures in the corona, but it's not quite clear yet how the turbulence evolves in these different coronal structures, and it's something I'm going to be looking into in the near future. So we can look at the sort of the nature of the turbulence that's propagating out of the corona. We can also use these waves for seismology and tell us interesting things about the plasma conditions in the corona as well. So on the right-hand panel, I just have three plots from a polar region, and this is again with comp data, and we can measure the outward wave speeds and the inward wave speeds, so waves propagating out from the corona, waves propagating back in. And what you can see in the two plots is that they have very different speeds. So the outward ones are moving much faster than the inward ones. You can ignore the yellow in the second panel. That's kind of noise that we're still working on at the moment. So you might think that faster moving waves outwards and slower moving wave inwards kind of suggests there's a presence of a flow there, which is what you expect in a sort of polar region. You expect an outflow. And so just by subtracting these two, you can get an estimate for flow speeds in the corona. And what I think this is showing is sort of the very young solar wind, where we can try and estimate the flow speeds for sort of the very young solar wind in the polar regions. And I know I'm running out of time, so if you just go to the last slide. As well as the flow speeds, you can also use the waves to determine the plasma structure, as I said. So what we can do with comp, as I show in the top left panel here, is we can measure the phase speed or the wave speed throughout the corona. We can also measure the electron density through the ratio of the two of the infrared lines. And then using sort of an estimate for the propagation speed, like a formula, you can relate this to the magnetic field. So CK here is the phase speed, and if we measure the density, you can relate it to the magnetic field, and you can actually get an estimate for the plane of sky magnetic field throughout the corona as well with comp. So here you're really able to define the sort of magnetic and plasma structure in the low corona, which hopefully is very useful for simulations as well as connecting it to the PUNCH observations. So last two words are, well, a few words are, comp is kind of gone now, and the instrument has just been upgraded to UComp. That's coming online. That brings about a couple of extra things. So we get a much larger field of view with UComp. We should be able to go up to about 1 solar radii, sort of look further out, define the structures further out, see how the waves are propagating a bit further out. And we should also get a range of coronal lines rather than just this single or this pair of infrared lines that they've been looking at. So it means we're able to examine the dynamics further out into the corona and also use the cooler lines that are available to improve measurements in coronal holes and hopefully provide some interesting information to go with what's going on with PUNCH. Thanks.
Thanks so much, Richard. Please put questions about comp and to Richard in the Slido. We'll get back to those during our discussion section. And now let's please hear from Roger Scott.
Hi, thank you. Can you hear me?
Yes.
Great, thanks. First of all, I apologize for the format. I prepared this as a poster and was not able, unfortunately, to update it, so I'll be brief. But the work I'm going to present to you is work I've been doing with Steve Bradshaw and Mark Linton, and this is an effort to better understand the hydrodynamic evolution of a newly reconnected open field line. I'm going to present it as a fairly simplified version in which we've tried to remove as many of the confounders that you might expect to be present due to the field line evolution of a newly reconnected field line. And so what we want to understand is, what is the hydrodynamic response? If we can better understand this problem, then we can hopefully disentangle more of those complicated influences in a fully dynamic system. So on the left here, I'm showing a figure that I've pulled out of a paper by Steve Bradshaw from 2011 that first introduced this configuration. And what we're thinking about is interchange reconnection between an open field line with a wind and a closed field line that is in a hydrostatic equilibrium. And we're going to model this using the Hydrad code. So this starts in a model chromosphere through a self-supporting transition region into the corona and out into the wind, into the heliosphere out to 30 R sun. So this is a fully self-consistent solution for the wind. And in the middle panel here on the top, I'm showing fractional ionization of oxygen. So this is oxygen 6 and oxygen 7. In the middle of the central panel, that's field aligned velocity. And then in the bottom, I have the density multiplied by the cross-sectional area of the flux tube. And so what we're going to do is concatenate a hydrostatic solution with a wind solution. And that's our proxy for an interchange reconnection event to form a newly reconnected field line whose material structure is hydrostatic below the reconnection site and then a wind solution above the reconnection site. And in the colored curves here, we're going from time equals 0, that's at the instant of reconnection with the black curve, and then out to 24 hours after the reconnection event, and that's going all the way out to the yellow curve. So what you can see is that at the instant of reconnection, we have a discontinuity in all the fluid parameters. That's density, velocity, electron temperature, ion temperature, and then the ionization ratios, oxygen 6, oxygen 7. Of course, we're tracking actually all the way from singly ionized to 8-time ionized oxygen, but I'm only showing O6 and O7 here because this is the ratio that seems to be most commonly cited as an indicator of open versus closed material composition. So what happens as this system evolves is the initial discontinuity first decomposes as a Riemann problem into a shock and a rarefaction wave. And this was not an unexpected result. It had been posited that it would behave this way. And then the rarefaction wave propagates down towards the chromosphere and the shock propagates out into the wind. When the rarefaction wave hits the chromosphere, it reflects and turns into a doublet of a trailing shock and a leading rarefaction wave. And then that rarefaction wave propagates outward. It eventually catches up with the leading shock. And then you have a triplet system, a trailing shock, an intervening rarefaction wave, and then a leading shock. And so that's shown in these blown out rectangular panels, for instance, in the field aligned velocity contour and in the density, where you can see the trailing shock, the outward propagating rarefaction, where both the speed and density increase with height, and then the leading shock, where the speed and density both drop abruptly onto the pre-existing wind speed and velocity and density. So one of the interesting features of this, though, is if we look at the oxygen ionization populations. So in the initially hydrostatic solution, the temperature and density are higher. You have a higher contribution from oxygen 7 versus oxygen 6. And then in the wind solution, it's the inverse. In this particular excerpt, so I've done a number of different studies for this, varying the location of the reconnection site. This one is taken at 2 solar radii above the transition region. That's above the freeze-in height, where ionization, recombination, and excitation, the timescales become very, very long. And so this feature just propagates out with the high-speed rarefaction. Below that, the ionization rates from the low corona have to pass through a region where ionization and recombination are still playing a dominant effect. And so that's why you see these curves go from black to orange, sort of sloping downward. Another interesting feature is that while the density and temperature are interacting with the compressive nature of the leading shock, once you get above the freeze-in height, the ionization ratios are advected as passive scalars. So they actually lag behind the shock front by a significant margin. So in this right set of panels, what I'm showing is the velocity, density, ion and electron temperature, and then 0.7 to 0.6 ratio at a fixed height of 20 solar radii. And then it's a time evolution on the horizontal axis. And then these different colored curves are for reconnection sites at 4, 2, 1, half, et cetera, all the way down to 1/8 of a solar radii. So this is our proxy for an in situ measurement, as you might imagine. So of course, the first signature of reconnection is the electron temperature, which gets a bump due to the hotter lower coronal material having advected or having transported heat by conduction out into the wind. And so you see that spike in the electron temperature happens very shortly after reconnection. Then you get a spike in ion temperature, density, and velocity. That's the leading shock front that arrives at a time that's governed more or less by the acoustic speed, right? So the shock is propagating at, let's say, Mach 2. And so that's when all those things arrive, is on a time scale given by roughly the acoustic speed and the distance to the site. Then you have the leading shock and then the slow decay of density, velocity, and temperature across the rarefaction, and then another little bump by the trailing shock. And then it steadies back onto a wind solution on a time scale of roughly the fluid transit time from the surface of the sun up to the height that you're interested in. The signature in the 0.7 to 0.6 ratio arrives much later because this is carried by fluid advection. And so in the strongest case, which is the reconnection site at 4R Sun, there's a huge discontinuity. The shock is huge to begin with. The speed in the rarefaction is quite large. And so that bump in the 0.7 to 0.6 ratio arrives pretty quickly and then eventually trails off slowly back to the original sort of quiescent wind solution. As you go down in height, these reconnection events have progressively weaker shocks and therefore lower speeds within the rarefaction region. And so the 0.7 to 0.6 ratio signature arrives later and later, lagging significantly behind, to the point where when we're looking at a reconnection event down at roughly, say, 1/4 of a solar radii, the hydrodynamic behavior has long since passed and settled back onto a wind solution before the actual ionization signature arrives. So, of course, there's a lot of caveats with this. We're looking at the most idealized geometry possible. We have a hydrostatic and a hydrodynamic wind solution, both along a spherically symmetric radial field line. We've taken as much of the geometry out of it as possible, just to understand the dynamics driven by the internal pressure evolution. Another issue is that the initial conditions are, as pristine as you can imagine. So there's no evolution being introduced into the fluid due to the sort of slow movement of a field line toward the reconnection site, or then if it were a snap away from the reconnection site, for instance. So we're assuming a very smooth, very laminar kind of model for reconnection here. But I think the takeaway is that there are signatures in both the hydrodynamic evolution of this N wave shock, rarefaction shock behavior, and then in the subsequent evolution of the 0.7 to 0.6 ratio as that's advected out into the heliosphere. I'll stop there, but I'll just with a quick plug say that this is soon to be published. So look for a more detailed description in September, maybe.
Thanks, Roger. So please put questions to Roger in Slido. And when we come back, we will have an open discussion with everybody. Thanks, Roger. And then right before the break, we're going to hear one more Sam Van Kooten.
Hi, thanks. I'll be talking, if you can go back, yeah, keep on that first slide for a
Sam,
second.
you're muted.
I'm
No, I
muted.
hear Sam.
Yeah, I can hear.
Sam.
We can hear you.
Okay. So I'll be talking briefly about some of the work that I've been doing with Steve Cranmer. I've been looking at the photosphere for all my work, but I'm going to tie that photospheric work to the corona, the heliosphere that everyone here knows and loves, as a way to illustrate one of many ways that photospheric observations can be very relevant to the big picture questions that PUNCH wants to address. And I'll be doing that by tying my work to this big picture question of how oscillations and turbulence evolve as they move throughout the solar environment. So moving to the second slide, I'll briefly summarize the work that I've been doing. With an eye towards upcoming DKIST observations, we're preparing to measure small scale wave driving on the photosphere. We'll be doing that by looking at photospheric bright points. These are some of the smallest features seen on the sun. They occur in the intergranular lanes, and they are the bases of flux tubes. And some of those flux tubes reach up to the corona, so they can serve as channels along which waves can travel. We'll be tracking bright point shapes and sizes as well as locations, and interpreting changes in those quantities as the driving of different modes of thin tube MHD waves. We're right now working with MIRAM simulations from Matthias Rimpel. These are simulations of DKIST-like resolution, and our technique should translate well to actual observations when they become available, hopefully in the next year or two. So moving to the next slide, there will be a plot that has all the stuff that I really want to show you here in this talk. There are 3 sets of power spectra on this plot. On the top third of the plot are the 3 spectra that we're producing, applying our techniques to those MIRAM simulations. Those 3 spectra are for 3 of those different wave modes. One of those modes has been studied in past work. Our contribution is adding the other 2 wave modes enabled by the higher resolution observations. In the middle third of the plot is our spectra from COMP observations of Doppler velocity fluctuations. And those are about 1/10 of a solar radius above the limb. And in the bottom third of the plot are a number of spectra of magnetic field fluctuations taken by Parker Solar Probe at a range of distances all the way up to almost a full AU. These are very distinct types of observations and measurements, but it's not unreasonable to compare them all. There's good reason to think that the waves driven by the bright points on the photosphere at least contribute to the full ensemble of waves being measured by COMP. And it's reasonable to think that COMP and Solar Probe are measuring, the same waves as they move through the solar environment, just kind of different sides of these MHD waves, whether velocity fluctuations or magnetic field fluctuations. So if we compare these spectra, the main thing to look at is the steepening of the spectral slope from about -1 at the photosphere to -1.5 in the corona, and all the way down to -5/3 out by about 1 AU. So that steepening of the spectrum as you move higher and higher from the solar surface, there are many ways you can interpret that, but one possible interpretation is that turbulence is active in different regimes. Wherever that spectrum is steepening, turbulence may be at play processing that spectrum and steepening it. I don't have answers here. This is again just an illustration of how photospheric observations can be very relevant to PUNCH, because PUNCH is of course very interested in how fluctuations evolve throughout the heliosphere, and PUNCH will be adding a lot of complementary data to this plot that I'm showing you here. And DKIST will of course be replacing our MIRAM spectra at the top with actual observationally sourced spectra. So this is my illustration of the connection of one of many connections between the photosphere and the corona, and this is what I have to show you today.
Thank you so much, Sam. And thanks for keeping to time. So please put questions to Sam in Slido. And what we're going to do now is take a 10-minute break. We'll come back in 10 minutes. So it's 2:30 if you're on the East Coast. So we'll come back at 2:40 if you're on the East Coast. And we'll hear 2 more presentations, and then we're just going to have an open discussion about everything we heard and any topics we want to revisit. So post in the Slido.